Hello, my calculus doing friends. Did I push start? I did. Okay, this is lab 3 and I told you that I would give you the answers to it. So I'm gonna work through the answers and we'll see how we go. The first thing I want you to notice is that finding a limit is like doing a proof. You need to convince me that the answer you found is the correct answer and not just a wild guess. And the other thing is it's asking you to find the limit using the limit laws and not asking you to use a table. And so sometimes people do that. They make this table of values or they just try to get really close to -2. And that's why a lot of schools will not allow you to use a calculator because that's not what we're looking for at all. We're wanting you to figure out what it would be. Now I notice that using the limit laws, the first limit law that I have at my disposal is that I can use substitution unless I have an asymptote or a hole in the graph. Then I have to work a little bit harder, right? And so the first thing I want to see is it okay? That's one of the limit laws, just to use substitution. So if I plug in that x is -2 in here, minus, and then -2 here, all over cubed -2 minus 3 times -2 squared. So this is the square root of 4, which is 2. And then 2 plus 2 is 4. I wouldn't have cared what the numerator became, right? I'm really concerned about the denominator. Is it 0? Doesn't look to me like it's going to be 0. Let's see, that's -8, right? -8. And then I have, this is 4, so -12. So this looks like to me that I have -20 down there. So this is -1/5. Okay, so my first limit law that I got to use was just shear substitution. Now it would be really nice if I got to use substitution on this. But when I go and I try substitution on this is where I get 0 in my denominator, right? When I plug in x is 0, 0 to the third minus 0 to the second times 3, that's 0. So 0 minus 0 is 0. So now I care what my numerator is. Is my numerator also 0? And the answer is no, it's not. When you plug in, the answer is the square root of 6, right? That's what the numerator is. So this tells me that I got an asymptote when the numerator is non-zero and the denominator is 0. And that means that it could be that it's positive infinity as our answer, or it could be negative infinity as our answer, or it could be does not exist. And I don't want to just guess at it, but those are the 3 choices if you have an asymptote. And because this one is from both sides, it's a possibility that it does not exist. So I want to look at the left side, and the left side looks like this, the limit as x approaches 0 from a little bit smaller than it. And I'm going to go ahead and I'm going to factor the denominator, just because that would make it easier for me to see what's happening. So I'm going to factor out an x squared in the denominator, and then this is x minus 3 here. So I already know that the one-sided limit is either positive infinity or negative infinity. I already know that because it was over 0. If I plugged in 0 here, again, I'd have the square root of 6 over 0. So I know the one-sided limit is either positive infinity or negative infinity. And now I just want to figure out what the sign of it is. So the numerator, when I'm a little bit before 0, this is really close to 0, right? But it's negative, but it doesn't overtake the 6 because this is really close to 0. So this piece is positive, square root of 6. And if I take away a negative value that's really, really, really small, then I'm still really, really close to square root of 6. And so all I care about is it positive? And the answer is it's positive. And then I have this piece and I'm squaring it. So no matter what you put in for x, when you square it, this piece is positive. And I'm putting in a negative value very close to 0. So I call that -0 is what I call that. So that's the part that is making it go to an asymptote, is I'm dividing by 0 right there, because this part, 0 squared, is 0. But this part right here is positive, and that's all I care about. Now, when I put in negative here, near 0, and I subtract 3 from it, well, I get something that's very close to -3, right? And so all I care about is the sign, and that is negative. So this part was the part that was 0, but you see how my sign is negative. A positive divided by, well, a positive times a negative is a negative, and a positive divided by a negative is a negative. So this is negative infinity. On the right side, so this is my verses, and on the right, right. So again, I'm going to write it in its factored form. If something factors, it makes it easier to think about on this. So for the same reason that the numerator was positive over here, the numerator is positive over here, because I have something slightly bigger than 0, but nearly 0. So this is near the square root of 6. And then I'm going to take away 0, right? Something just very near 0. So it's positive, right? Square root of 6 overwhelms it if it's very near 0. So it's positive. And then I have something squared. No matter what I put in here, it's going to be, do you guys agree? It's going to be positive. Well, that was my part, was positive 0, right? But still, it's positive, right? That's the part that's making it infinity, is dividing by 0. And then this part right here, when you put in something, you got 0, and you take away 3, well, that's negative, right? Very close to -3. So for the same reason that this was negative infinity, this is negative infinity. It was because of this square that they're the same. If it wasn't for that square, they would have been different. So the limit that we were asked here as x goes to 0 of this function is negative infinity, right? It's approaching negative infinity. So that's what they were asking us to do on that. And then this one here, when I go and I substitute in, right, I'm going to get the square root of 3 plus 6 minus 3 over, and then 3 cubed minus 3 times 3 squared. And see, that's going to give me 3 minus 3 is 0. This one's 0 over 0. And so that tells me indeterminate. And that means it's probably a hole in the graph. Most likely it's a hole in the graph. So I've got to, so now I'm going to have to work a little bit harder. And how you work harder when you have a square root that's involved in a binomial is by multiplying by the conjugate. So I'm going to have here the limit as x goes to 3, and I'm going to multiply here by the conjugate. So that's my story. Now I'm hoping to cancel that denominator, and I'm hoping to make this numerator look nicer. So I am going to be multiplying in the numerator in hopes of making it look nicer. There's the conjugate when you change it to from a minus in between to a plus, right? So I'm multiplying by the conjugate here. I got the hungries. What did I have for lunch? It's an answer to a question that I don't know. Maybe I didn't have anything. Maybe I did have something. So when I multiply this together, because I multiplied by the conjugate, you would be doing FOIL to multiply it together, but the outer and the inner, when you multiply by the conjugate, becomes 0. So all I have to do is worry about the first and the last. So the limit as x goes to 3, and then I'm going to have here x plus 6, right, because they're the same, and then minus, right, there was the first, and here is the last, minus x squared. All over this darn stuff. X cubed minus 3x squared times this over here, which I do not want to multiply together because remember I wanted to cancel something from there. And in fact, I know what I want to cancel. I want to cancel the part that's making when I go to 3 it be 0. So I want to cancel x minus 3. Is what I want to cancel, because that would be making this go to 0, right? So I'm sure that that's going to be there. And so So in my numerator, I'm on factoring, and I can factor my denominator. I can see that this will factor, right? I already factored that up here, and so it's going to be the same. And this numerator, I can see that it will factor too. So I'm going to get my factoring out here. This is negative x squared plus x plus 6. I'm going to factor out a negative 1. So that's x squared minus x minus 6. And then I'm going to get here my binomial. Let's see, it's going to have to be minus 3 and x plus 2, right? So that's how that would factor. If you're having trouble factoring trinomials, I probably was having trouble factoring trinomials when I took Calculus 1, and I didn't have the opportunity to go get help on Khan Academy, and you do, and so you're pretty darn lucky. And so he factors all kinds of trinomials and tells you all different kinds of methods of factoring them. And I just use unfoil is the method I use. So any method that you want to use. So I basically was saying to myself, what would make the x squared? Well, x and x. What would make 6? Well, 2 and 3. What would make when I combine them negative 1? Well, it had to be a negative and a positive. So, so it's kind of a little trial and error almost. I call it unfoil. And so you can use whatever you want. So there's people that like to use the diamond method, and there's people that like to use the box method, and I'm like, okay, that sounds great. So when I factor this, remember I was going to factor that x minus 3 here, and then that crazy square root, friend. And that crazy square root is no longer 0. Do you guys notice that? When we had the conjugate, it was 0. Right? But because we changed this to a plus, instead of being 3 take away 3, this is now 3 plus 3. So it's no longer the problem of being 0 now that we got it. So it helps in a lot of different ways. So here's the part that was making the 0 over 0. There it is, dividing out, going away there. And now I can use substitution with what I have left, the limit as x goes to 3, of negative 1 times x plus 2 over x squared times the square root of x plus 6 plus x. So now I can substitute in. Now I am finding the limit. Now I am substituting in. Remember, finding the limit, the number 1 limit law is substitution, right? And so I now can substitute in because I'm not having divided by 0. And so in the numerator, when I substitute in, 3 plus 2. I'm writing out that I'm substituting in, although I know people could probably do that in their head. And the reason that I'm writing it in is so that people know I'm serious. I'm substituting, right? So in the numerator, that's negative 5. In the denominator, that's 9 times, and then 3 plus 3, which is 6. So this is negative 5 over, is that 54? And that's what we get. So we did a lovely job on it. I think that was the hardest problem on the lab, definitely. And this was a problem on homework. So people ask me, where did you get that horrid problem? And almost always the answer with me is, well, it was a homework problem. And so they say, and so now they're looking and thinking about y equals this same thing that we were just looking at, right? The same thing we were just looking at. And they say that they have the graph below. So there's the graph below. They graphed it for us. It was really nice of them. They say, hey, there's a hole in the graph at, and where's that hole at? Well, friends, the hole comes right here. Remember, 0 divided by 0 is most likely a hole. And if you can work it down and get a value like this, it doesn't turn into an asymptote, then it is a hole. So the hole happened at x is 3 and y is negative 5 over 54. And they ask us to go put the hole on the graph below. So right here is 3, and the hole is right there on the graph below. And so you can kind of see that this is where negative 1 is there. And so this hole, and I tried to make it not look solid. And so I'll make it not look solid. So there's a hole in the graph right there. So there's a little hole in the graph. Okay, then it says the graph has an asymptote. Well, we found the asymptote, right? Remember we said, hey, there's an asymptote. Where's the asymptote at? Well, it's at x equals 0, because that's what created this asymptote, is when we got close to 0. So the asymptote is at x equals 0. And yes, you do need the x equals part because it is a vertical line. So if you just put 0, then you have not put a vertical line. And then they asked us to go put a dotted line where the asymptote is. So here's the dotted line at x equals 0. And you can see that the two sides, remember we said that as we got closer to 0, that it was going towards negative infinity. And so you can see that it's going towards negative infinity, right, as it goes off the graph there. So we did that. So we put our dotted line to show our asymptote, dot, 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 there it is. Okay, the graph seemingly ends at x equals negative 6. So right here, they're saying that, hey, it looks like it just ends right there. What's the deal with that? And they wanted you to talk about that. Why does it seemingly end? And so we look back at our equation to see if we can get any hints at why it might just end abruptly at negative 6. And do you guys see the problem that right here, the square root, right? You're not allowed to have the square root of a negative. So this is the problem, is that x plus 6 needs to be greater than or equal to 0, right? Because can't take the square root of a negative. And so that means that x has to be, if you subtract 6 from both sides, greater than or equal to negative 6. And so you notice that it just abruptly ends right there at negative 6, because I'm not allowed to go over there. This is the domain, right, of my thing. Now, it's not all the way my domain, because I haven't taken consideration some things that I should throw out as well. Do you guys know what I should be throwing out from the domain? Right? X would not be okay to be 0, and x would not be okay to be 3. Do you guys remember that? And so, so if I wanted to state my domain, it's going to be that x has to be greater than, I didn't ask this, but x has to be greater than or equal to 6, and x cannot be 0, and x cannot be 3. So those would be the things, and they would probably in your book throw some fancy set bracket stuff, x such that, and then these conditions about x, right? And so, but it didn't ask you for the domain, but then the minute I wrote that this is the domain, I realized, oh, wait a minute, I need to throw some things out. Now it asked me to talk about the continuity and write the interval for which it's continuous. So it starts here being continuous at negative 6. So continuous. And so it starts at negative 6, and it includes negative 6. So I wanted to have a bracket like that, and I'm not going to be able to handle that I didn't make it look too good, and have to go and fix it, because that's just how I am. And it's going to go until x is 0, right? And then they usually in your book use a comma. And so people have been asking me, would it be okay to use the union symbol instead? And I've used another textbook that used the union symbol. And I told you guys I was going to ask Arnie his opinion. And so I'm using a comma just because the book did. And so, and this is going to start again at 0. And then we're going to toss out 3. And so comma. And then it's going to go to 3 to infinity. And always parentheses with infinity. So this is this is continuous on this interval. It's continuous on this interval. It's continuous on that interval. So 3 intervals that it's continuous on. So there we did a lovely job on number 6. And now we're off to number 7. And it says, for what values of the function of x is the function discontinuous? So it's discontinuous. My graph is kind of blurry, and it looks like counting by 1. So at negative 1, so we have a discontinuity at x equals negative 1, and we also have another discontinuity at x is 1. So we have a little hole in the graph at x is negative 1. It's kind of blurry. and we have a jump discontinuity here at 1 and no other discontinuities. And we don't know if this ends right here or goes on. This graph came from the Stewart book, and sometimes I look in the back of the book and he has it, answers the questions as if this was a hard circle like this. So as if it ended there. And sometimes he answers the questions as if this went on. And there's no way of predicting what he's going to do. And so if I could do anything, it would be to get them to either put dots or arrows going on. We're going to consider it on this problem to be hard dots there. If I don't go in and fix it, then I have to take either, is what I think, because that's what the book kind of goes on. On what intervals is G continuous? So this is G. And so we have, and we're going to say that it starts here at -3. So at -3 to -1. So it's not continuous at -1. And then -1, and I put union, and I told you guys I was going to use the comma because the book did, our book did. But I noticed that WebAssign took either to 1, comma, and 1 to 5, and includes 5, right? What is the domain of G? And so some people say, well, isn't it just this, the same? And the answer is not always. So like we had a problem at -1. It wasn't continuous at -1, but is -1 in the domain? And so what you're asking yourself, when you ask yourself if -1 is in the domain, can you find G of -1? Or will you say it's undefined? Well, I see it's 3. So that means that -1 is in the domain. And the other problem I had was at 1. Well, do you know what G at 1 is? Yeah, it's 2, right? And so these are not domain issues. They were continuity issues, but they're not domain issues. So actually the domain is from -3 to 5. No points are left out. Of every value from x is -3 to x is 5, we could say what the y value is and not have undefined on any of them. And then what's the range? So the range is looking at, well, is everything taken in consideration? So I'm looking here, the lowest here is 2, and it's open, but 2's filled in right there. So if I told you that y was 2, you could tell me what x is. X is 1, right? And so 2 is part of the range. And here, that does no help, right? And I have an open here, but it's closed over here. So that means 4 is closed up. And it looks like it was open here between 4 and 5, but you see how it's closed up, it's taken in consideration. If I asked you, y is 4.5, what's x? You could tell me what it is. So y is 4.5 is part of the range. And what about 5? Well, 5 seemed up there. So I think that it goes from a low of 2, the y values, of 2, it includes 2, and goes to a high of 5. So the range is 2 to 5. Show that G is discontinuous at x equals -1 using the continuity checklist, which you can find the 3 conditions which of the 3 conditions I said are violated, 1, 2, or 3, and you can find them at the top of page 83 in your textbook if you have the textbook. So condition 1 is that G of -1 is defined. And that's certainly true, right? This is true because we found G of -1 is equal to 3. So it's defined. So it doesn't violate condition 1. And then the limit as x approaches -1 of G of x would exist. Exists. And so this is a question mark. I haven't checked that yet. This one I'd already checked. So let's go see if the limit exists. So as I approach -1 from either side, right, getting closer, what is the limit value? Well, it's getting closer from both sides, the left and the right side, to 2. So this is a check mark. True. It exists. It is 2, right? True. It was defined. It is, what did we say it was? 3, right? So those things are check mark. The third says that this, the limit as x goes to -1 of g of x, would equal g of -1. And that's where we know one of them's not true. I told you it was discontinuous, right? And so that means it fails one of these 3. And since it met the other 2, it's got to fail this one. And we can see that it does because we know that this was equal to 2. And this is equal to 3. And so they're not equal. And so I asked you, so this is your showing of it, right? It violates condition 3. So it is discontinuous, it violates condition 3, and that's all that I was asking you to show. Show that G is discontinuous at x equals 1 using the continuity checklist. So we're going to go do the same thing. G of 1 is defined, right? Check mark, G of 1 equaled, we found it up above, 2, right? So this is true, doesn't violate this. The limit as x approaches 1 of g of x exists. And this is where I'm asking myself, question mark, does it exist? So I'm approaching 1 from either side of 1. So if I'm on the little bit smaller than 1, on the left side here of 1, it looks like it's approaching 4 to me. But on the right side of 1, it looks like it's approaching 5. And so this is where we get our problem, right? And so I'm going to just tell people that the left limit is 4 versus the right limit is 5. So this doesn't exist. So it violates. So that's why. So this does not exist. So it violates condition 2, which is that the limit exists. It doesn't exist. The limit does not exist. So which of the discontinuities is a removable discontinuity? So we have 2 of them. And the one that's a hole in the graph is removable. If it's an asymptote, it's not removable. And if it's a jump, it's not removable. This one doesn't have an asymptote. It has a jump though. So that one is not removable, where this is a hole in the graph. So it's the one that's removable. So it asks you which one of the discontinuities is removable, and that's the one that's at x equals -1 is removable. How could you redefine the function at that point to extend the continuity, to make it continuous? That's what it means. So it basically means, what would you have to do to make this continuous? Well, that would be to fill in that hole, okay? And then it would be continuous. And they disregard that totally. And so all I'd have to do is fill in the hole. I'd have to redefine g at -1 to be equal to 2. So if I did that, so redefine, so g at -1 would have to equal 2. So this would be my redefinition, and then it would be continuous. What type of continuity, I can't talk, do we have at x equals 1? And it is, we've talked about it before, it's a jump, right? Okay, so that's your lab number 3, and so I'm going to post this for you, friends, and I'll talk to you later. Bye-bye.